So can you hear me? Is it working or not?
Yes, we can hear you, Mr. Pietro. It's working.
Good. So
yeah.
Nice to meet you.
Yeah, nice to meet you. You can start your webinar now.
Okay, just 1 second because I don't know how to share my screen.
Okay, you can
because I see your screen now.
Yeah, you can see the green panel at the bottom. It said share screen. Yeah. Okay. Yeah.
Continue. Desktop. I think is this one. Share.
Yeah.
I have to allow this software to share my screen. Just a second.
Okay.
Yes. I have to go out to be able to share my screen, and then I will join again. Give me just 1 second.
Okay, Mr. Pietro.
Sorry.
Dia mesti lockout dulu sebentar. Transfer lagi. Dia mau ambil PPT-nya dari komputer lain. Sorry, dia mau share PPT dari komputer lain. Lagi.
Okay, let's see if I can do it now. This will stop the screen sharing. Yes. Okay. Share. Okay, now it's working.
Yes, it's working now. Okay.
Okay, so maybe just to maybe it's better just to do like this. Okay. Okay, so I will start with this would like to be a very concentrated seminar, okay, because we don't have so much time. So my idea is try to put some very let's say milestone on different technologies. Okay, with different technologies, I mean I'm speaking in a certain word, which is the biodecontamination, okay, or sanitization, disinfection, sterilization, you can call it as you like, of space, enclosed space, closed area. So that could be a clean room, that could be a laboratory, that could be an isolator, that could be a pass box. So any enclosed space that requires decontamination, so to get the microbiological reduction of the surface microbes contamination. So actually, I will only speak about the H2O2, so hydrogen peroxide decontamination. It's important to underline because there are various methods for doing decontamination, but we will be concentrated mainly today to H2O2. So hydrogen peroxide is a molecule very similar to water. So the behavior from the physical point of view is the same, okay? So I just would like to underline that there are, like water, also the hydrogen peroxide can be found in two different state, which is liquid and gas. So if you take water as an example, water can be liquid, so the water glass, okay, the glass of water that you drink, or water can be gas, and in that case is in the air, and it's the relative humidity. So that's an important distinction because many gas does not have the same behavior. You know that some gas, like oxygen, is only gas state, while other let's say other molecular like water is not only gas state but can be also liquid phase. Okay, so H2O2, the hydrogen peroxide molecule, is very similar to the water molecule, and it can be found in those two different conditions. That could be gas or liquid. So accordingly to the way you apply H2O2 on your enclosed environment, you can have different technologies. So there are technologies that apply H2O2 in vapor, and you can clearly see that it's, I would say, it's like a smoke, so that definitely it's a gas, okay? And there are technology which applies H2O2 in liquid phase, so like small droplets of aerosol. Both technologies are available on the market with different price and different, let's say, supplier. From my point of view, it's very important today to learn how to distinguish and to understand which are the differences between those two technologies. So I would like to start from the book definition, okay? Any physics book or any, let's say, book that treat that kind of matter will give a different definition, but I made a summary which can help us to better understand what we talk about. So basically in a vapor, what is a vapor? Is a gas, okay? So the vapor is a gas which has a very particular characteristic. So this gas can condense, so can come back to the liquid state if you increase the pressure without modifying the temperature. Okay, so this is the real characteristic of a vapor. And in real gas, like I told you before, oxygen, to give you an example, the oxygen is a true gas and cannot come back liquid to ambient temperature. No way. You can increase the pressure of the oxygen, you can increase the quantity of the oxygen, but you will never be able to have liquid oxygen at room temperature. To make liquid oxygen, you need to go down with the temperature, minus 200, whatever. I don't remember exactly the temperature, but you need to go down up to a point where the oxygen can come back to liquid. So in case of water, for example, or in case of hydrogen peroxide, again, H2O2, you can have at the same ambient temperature today, you can have your glass of water, liquid, and you can have the water into the air, which is relative humidity, okay? And it's a gas. So it's important because we will see in a minute this exchange of, let's say, status from liquid to gas and from gas to liquid is regulated exactly from this pressure, which we call it relative humidity. Okay, when relative humidity is the pressure of the water in gas state against the liquid phase. So when you increase the relative humidity, of course, you have rain. So when you have 100% relative humidity, everything gets wet because of this phenomena of changing from liquid to gas. Different story is the aerosol, which is the one I showed you before, aerosol here. And aerosol is a way to apply the H2O2 in liquid phase. So we don't apply it in vapor, in gas, but we apply it in liquid. So tiny, small droplets, so small liquid droplets, okay, which are dispersed. They are, you make a dispersion into a certain volume, basically. So this dispersion can be done in different way. The most common is driven by air, but it could be done through, for example, electrical piezo, which is ultrasonic, okay, dispersion. It generates droplets. It can be done through very fast rotation speed. It could be done through compressed air and small nozzle. All these methods always gives you small droplets of liquid within your gas dispersion, okay? Now, it's important to distinguish because, of course, like everything in life, there are advantages and disadvantages of the technologies. Now, in case of droplets dispersion, the aerosol, okay, so in that case, you don't need to take care about the relative humidity because it's already liquid, will not condense, it's already condensed, okay? While with the H2O2 vapor in gas phase, it's important to take care about the relative humidity because you can have a change in the status from gas to liquid. But of course, there are also problems with, again, advantages and disadvantages with the spray system. So I don't want to, again, be too much pushing in one or the other direction. I just want to underline from our point of view, which can be the limit of the aerosol technology that can be overcome by the gas technology, okay? This table would like to help summarizing a little bit which are the differences from the technical point of view. And the H2O2 liquid, so the aerosol generator, there are different names to describe accordingly to the supplier, accordingly to the method of droplets creation, okay? So you have different kind of names, basically. And H2O2 gas or vapor is as well. You have different name according to the supplier, according to the let's say, in that case, it's not the method because the H2O2 method to make it vapor, to make it a gas from a liquid phase H2O2, there is only one method. You need to heat it up. Okay, you need a temperature to vaporize. So the method in that case is always the same to generate the gas. While here, the method to generate the droplets could be, as I told you before, different. So in case, anyway, all different suppliers, they named in different way the gas coming from the H2O2. So the first issue, or I would say the first difference, okay, in the dispersion is the dispersion of the biodecontamination agent. So if we talk about the liquid, so the aerosol generator, the small droplets, the diffusion in your area, of course, these become more critical as soon as the area is bigger, okay? The diffusion depends on the droplet size because big droplets will be much more heavy and will fall down, okay? When if the surface, big droplets immediately destroy on the surface and everything comes wet. While where the droplet is very small, usually it's, I speak around less than 10 microns. There are some bouncing effect on the walls, so the distribution is better. And because the droplet is very tiny, very small, it can, you know, go farther because it's lighter. So this depends on the droplet size, the weight, of course. Depends from obstacles, because if you have a barrier, the droplets cannot overcome the barrier, okay? You will create a shadow effect. And it depends from initial velocity. Of course, if I have no speed, the droplets will not go farther, you know, it will fall down immediately. So you need also speed. This formula is a little bit difficult, but this is the formula of the expansion, the distribution of a gas into a space. And basically, I don't want to go into the mathematical of this because I have no idea. Okay, I just copy paste. But what I understood is that depends basically on the time. So the real problem when you have a volume, those numbers only depends on the kind of molecule you take into consideration. So oxygen will have a time of expansion. H2O2 will have another time of expansion. If you take a nitrogen, will have another different time of expansion. But the only point is the time. So if you wait long enough, every single point of your area will be reached. It doesn't matter how complex it is. It doesn't matter how many obstacles you can find. It's a gas. It will be sooner, it will be later, but every single point it will be reached. Corrosivity. This is a big issue. Again, I don't want to point too much on one or the other technology. There are some facts. Most of the aerosol generators, so most of the technology which use the droplets sprayed, they have a mixed compound, not only H2O2, they mix with other chemicals like peracetic acid or silver ions, whatever. And this combination of different molecular could be potentially more corrosive than only the H2O2 alone. Definitely, like every chemicals in the world, the corrosivity depends from the concentration and the contact time. That's it, you know. So long contact time, high concentration, more corrosive. Less contact time, less concentration, less corrosive, but still corrosive. Okay. Vapor phase is a little bit tricky because the gas itself does not corrode. You know, the gas, as by definition, by definition. But if you only need to take in consideration water, I will give you an example in a minute. The gas water doesn't cause any problem, while the liquid water it causes. So the gas is definitely no corrosive, basically. There is a but if you condense. Of course, I told you before, it's a gas, but can come back to liquid. So liquid phase again could be corrosive. So you need to really take care about the gas equilibrium. Residues after cycle. Whenever you do the cycle, at the end of the cycle, you need to remove all the gas or the liquid that you introduced in your volume. The gas will never leave any residues because it's a gas. The liquid, it depends from the chemical composition. If it is a Wi-Fi water, poor, ultra poor, with no residues at all, there will be no residues. But if you use other compounds like the H2O2 as a stabilizer to keep it stable, then you will have maybe really small residues, but something that you will have on the surface. This is an important matter, at least if you work in a sterile area, I mean Class A, Class B, pharma production, aseptic production. Then when you spray substances, it comes back in the area of sanification, disinfection, so it should be sterile for the GMP, if you follow the GMP. But while when you work in the gas phase, no, the H2O2 liquid does not need to be sterile because you have evaporation process. So you have a gas at the end which has no residues. That another important point is the HEPA penetration for those who works with vaccine, for example, or for those who works with biohazard application like safety cabinet or biosafety laboratories, whatever. Whenever you have an HEPA filter and you want to change it, you need to gas the filter before to remove for the operator safety. And whenever you have the aerosol, you have droplets. And I told you at the beginning, you know, the droplets are around 5 microns as a dimension. I mean, 5 microns is big for an HEPA filter, because the HEPA filter will stop everything more than 0.3 microns. Therefore, the droplets generated from an aerosol cannot penetrate the filter, will not have that ability, because the filter will stop everything more than 0.3. While when you have a gas, then yes, the molecule is really small. So you don't have a droplet size, you have a molecule, it's a gas. So we'll penetrate the filter straightforward as far as you have a stream of air. Last but not least, even this is a big discussion, but okay, we can discuss, at least in my experience so far, the efficacy of sprayed H2O2. I don't mean efficacy in one point, but take in consideration what I told you so far. If I take a room or an isolator and I put a real test with biological indicator with a most resistant spore, the H2O2, which is the sterile thermophilus spores. And if I use enough quantity of biological indicator, and if I do that test several times, 2-3 repetitions to prove the repeatability, reproducibility of your cycle, usually I would say 90% of the, or if not 100% of the sprayed technology cannot get more than 5 log reduction, at least in the average, while with the gas, you can get always 6 log. There is also a simple reason. Most of the spray works with a low concentration H2O2, 6, 7, 8% H2O2, while the gas works with a 35% H2O2. So the concentration is higher, more ppm, more ability to kill. Now, I would like just to very shortly go deeper on some of those points that can be maybe more difficult to understand from a physical effect point of view. I tried to put simple, let's say, screenshot, okay, to make it easier to understand. I don't pretend to be scientifically accurate. I just want to give you some image that helps you to understand some point, okay? So those are 2 iron nail, the one that you use to fix in your house the painting. Look, this is what I want to transfer to you: a liquid against the phase. What is the corrosion? So if you look to water, the effect is pretty clear. The computer that I am using in my office now, it's surrounded by water all its life. And there's no problem because it's gas water. It's the relative humidity that I have in my office. This iron nail is surrounded by water as well, you know, all its life. It's again gas water, relative humidity. But as soon as you put the liquid water in contact with your computer or in contact with the iron nail, then you get the rust or you get the damage. So this is not due to the nature of the water molecule, is due to the differences between liquid and gas phase, okay? That's the point, you know, H2O2 is the same. I don't want to say that H2O2 is not corrosive. That's not true. H2O2 can be corrosive, 100% sure. It's a corrosive liquid. The point is, If I have to make a choice, I would try to keep everything in gas phase as long as I can. Of course, as I told you before, and again, I want to be politically correct and not to push too much on one or the other technology. If you don't control the relative humidity properly, you condense 35% H2O2. When you spray H2O2 liquid, as I told you before, you use around 6-8%. So the concentration is lower, the risk is lower. So I would say the best in the scale is to stay in gas, and if you cannot, then use the less concentration possible to avoid, corrosion effect. Again, don't pretend to be scientific, just to give you some impact, picture and switch up some lamp. That's another very easy to understand phenomenon, okay, which is the shadow phenomenon. Whenever you have droplets, okay, again, it's not scientifically true because those droplets are really big. It's the rain droplets are big. It's not 5 microns, okay? But anyway, it's pretty easy to understand that whenever you have a direction, whenever you have a direction of a droplets and you find an obstacle, there will be no way to avoid a shadow effect on the other side. Okay, that doesn't happen with the gas because the gas has a different movement in the air because it works with the Brownian motion. It's a molecular which is moving very, very, small, less than a nanometer. Therefore, the movement is Brownian motion. So it's moving by itself. Whatever bigger than a micron has no Brownian motion. So it's just driven by the gravity or the speed. So those are the reason why, it's important to distinguish between those two technologies. Again, just to close, because I don't know how much time do I have more than this, but I want to leave maybe space 5 minutes if there are any questions. From my point of view, it's important because there are applications where this technology is okay. Should be used from my point of view. While there are other applications where the vapor is better from application point of view. So it's important that anyone understand those are two different technology and are needed for different applications. Should I cover any other topic? I don't know how much time do I have because I don't see any counter on my screen. Maybe it's nice to leave some question. No? When I see I still have time. Let's see. Time maybe to show you something else. So no question. So I go on, and then when you want, you can stop me. Like I told you before, there are different, different technology, different possibility. I mean, biodecontamination or sterilization you can do through temperature, you can do with the gamma radiation, you can do with chemicals. Those are all nice methods, okay? But you cannot put your clean room into an autoclave. So the dry heat or the autoclave, the temperature method doesn't fit the room. Same with gamma radiation, okay? So that doesn't mean that the autoclave is not good, it's the best. But some application you cannot use it, okay? So same from my point of view for that story. Some applications are not good for the fogging system, and VHP is better. One thing I would like to because again there are no questions, so I go on. One other thing that is very on my heart, I would like really to give you is that specific slide. I tried to justify why the gas, why the H2O2 should be used, okay, against many other molecules. And what I would like to put on your attention is that those are, you know, different limit, different, let's say, characteristic of every molecule that you can find on internet. And it's important because when you go look to the H2O2 gas, there are some parameters like the short-term exposure limit, or the TWA is like long-term exposure limit, okay? And you see that the molecule is very, very safe. Look to the ozone. That's nice, you know. Now for this in this period of time, there is a lot of people that speaks about ozone to do sanification of rooms, whatever. And there is a Q&A. Let's see. Why I cannot see this? I see there is a question and answer, but I cannot click on it. Sorry guys, I see there is a question and answer, but I cannot, don't know why I cannot visualize it. So if anyone has a question, switch off the microphone and speak. I don't know why I cannot see the question and answer. So important is basically the H2O2 is safer, you know, even safer than the ozone, because the limit, short limit for the exposure of the operator is 75, while the ozone is 0.3. So it's 700 times safer than the ozone. You can find ozone, you know, online and buy for very cheap money, but it's a dangerous molecule. So that's why H2O2 is so important. That can be either in gas or vapor phase, in vapor or in spray aerosol. Okay, but it's a real important molecule to be taken into consideration. Okay, if you look to formaldehyde, which is very used worldwide still, you see the limit is much lower, 2 ppm against 75. But most important is that it is cancerogenic for human. Has been recognized to cause cancer on human. Okay, while H2O2 has been investigated and recognized to be absolutely safe, and the class 3 means it does not cause any cancer, sure, 100%. So it's really important also to whenever you choose for a technology, or whenever you choose for a specific molecular for your process, for your decontamination, to take in consideration the safety aspect, not only the brand name or the efficacy or the price. Okay, really important to take in consideration the safety aspect. Okay, and then H2O2 again, it can be liquid or phase or vapor, but still it's H2O2. It's not formaldehyde or ozone or other molecula which are listed here that has other ring points of concern. Let's see what else I can tell you. This is where I took all the information. You can go on those websites and you will see that what I told you is exactly same reported in those websites. There are some, like ethylene oxide is widely used in the medical field. So it's another very widely used sterilization method. But now, for example, all the ethylene oxide sterilization is going in the next year to be substituted with, from ethylene oxide, they are changing to H2O2 gas under package. Please.
Yeah. Hello, Mr. Pietro.
Hello, Lisa.
Yeah, you can hear me?
Yeah.
Okay, thank you. I'm the one that typing in Q&A box, but you cannot read it, right?
I don't know why. I tried to click several times, but I cannot see anything.
Okay. Actually, I would just like to ask: is there any standard procedure that stated which one to be choose between the H2O2 vapor or gas method for the decontamination of the clean room? Is there any specific standard mentioned about which method should be choose?
Yeah, I will show you. So basically, now I open the panel and then I can know how to close it. Okay. So basically, there is no a real regulation that tells you exactly which one you should choose. Again, from my point of view, it's like for the autoclave or the gamma radiation. There is no regulation that tells you if your sterile garments for the clean room should go into the autoclave or to the gamma radiation. But you cannot put the garments, you know, the clothes into the autoclave, will be destroyed. So you go for gamma radiation, okay? So one thing is the logic. So for example, to stay on the fogging or the vapor phase, whenever you have an isolator for production, you must be sure to get a 6-log reduction everywhere, in every point, in every corner, no shadow, no residues. It must be a gas, okay? Whenever you have a room, that could be a discussion, for example. One good point is, for example, in places where you cannot stop the ventilation system. Because, you know, the ventilation system, when I have a gas, I generate the gas and the ventilation brings the gas out. If I have a spray with droplets, I can maybe overcome that issue. So, for example, in places like hospitals or like some laboratories where the ventilation cannot be stopped, at least you can do a decontamination. With the gas, you cannot. There is also some important point. Let me see. No, it's not here. Sorry. Okay. One other important point is this one. So if you look to most of the international regulation, at least for looking to pharmaceutical field, so the GMP, you look to the FDA, APA, they mostly speak about vapor phase hydrogen peroxide. So hydrogen peroxide applied in vapor phase. But to be honest, they speak it in relation to surface sterilization. So my criteria is whenever you need a surface sterilization, and this should be approved from your regulation body, then, you know, vapor is the right. It's written in the regulation mostly, okay. Whenever it's not that mandatory, then it's a discussion that you can do with internally to better understand which is the best approach for your specific process.
Okay, Mr. Pietro, I can get your point. So it has some international standard, but of course, the exactly option that you could choose is based on the risk assessment of your target, right?
I would say really it depends from the application, and with application I mean wide concept, you know, the market where you are talking about pharma, talking about hospital, talking about other markets, laboratories. That could be the application, means the real application. We're talking about rooms or isolators or a freeze dryer, for example. And then also which regulation you are subjected to and which result do you want to achieve, and the condition of your environment. Another good example is the temperature. There are applications where the temperature must be very low. One typical example is food. Whenever you need to treat food decontamination, usually they work in atmosphere that are 4 or 5 degrees C, very, very cold. No way to apply the VHP because the gas will condense in liquid immediately. It's too cold, you know. You generate the gas and the gas boom, liquid. So those conditions, for example, it's very good to work with spray application because there will not be a problem. It's liquid already. It's not depending on the temperature anymore.
Okay. Okay. Thank you very much, Mr. Pietro.
It was my pleasure to answer you. Okay. So that would be great if you have any other questions. I was just willing to show you these maybe let's see. Another good topic, I don't have a slide for this, but another good topic is the compatibility, not compatibility with the gas phase or the liquid phase. But you should remember that H2O2 is not only corrosive, is a molecule which is a reactive chemical. So H2O2 can oxidize or even do reduction. So it depends from the condition where it's placed. So the H2O2 molecule is very reactive space. So reactive species of oxygen, ROS. So that's important because sometimes, you know, we come back to this slide. Sometimes the H2O2 is not the right molecule. This is not, doesn't depend anymore liquid or gas, but it's H2O2. One good example is insulin producer. Whoever produced the insulin knows that this specific molecule, insulin, is really sensitive to the H2O2. So it's enough, few ppb part per million of H2O2 in the air to destroy the insulin into the ampoules. So you know, there's no way to use it for sterilization of that specific product, for example. So there are situations where there is a conflict between the product that you are going to produce and the molecule itself. Sometimes there is a conflict with materials that you have in room. Usually not, you know, it's very uncommon, but that could be some specific painting, maybe special painting in the walls, or some specific coating. For example, there are specific aluminum coating which are not very compatible. That means whenever I use the H2O2, it doesn't matter, liquid, gas, it's enough to be H2O2 as a molecule will react with that specific material in a chemical way, no? It's a chemical reaction, and that could be an expected result. For example, a couple of years ago, I did a study for a company manufacturing anodized aluminum, so aluminum with a color coating. And they had they were working in the pharma field, and they had a hard time to find out the right coating, because it looks like most of the coating of the aluminum get discolored by the H2O2. It doesn't matter if you use the liquid or the gas. I mean, it's the H2O2 slowly take out the color from the aluminum. Then you have a gray aluminum, no problem, you know. But if you want to sell a blue aluminum and then it comes back to gray, that's not good. So,
Mr. Pietro,
sorry.
Just, I'm afraid your time is up. We need to start another seminar.
Okay, great.
Sorry, Mr. Pietro. Okay, thank you, Mr. Pietro.
Thanks so much. It was a pleasure.
Okay.